Okay guys, so we got a slightly shortened class today, so we're going to need to work fairly quickly on this activity, but the good news is that the data collection shouldn't take us very long, okay? So we got a couple of things here that we need to do on this activity. We're trying to figure out how much of the mechanical energy, both kinetic and potential, of an object is conserved during a mechanical energy conversion. So we'll be looking at the conversion of the potential energy of the cart at the top of the ramp into kinetic energy of the cart at the bottom of the ramp. Okay, so we're just looking at that part of it. We are going to do some measurements after the bottom of the ramp as well, but they're more for like a friction kind of review. Okay, and that's, we obviously know in that part the kinetic energy is being converted into heat and sound, whatever. Okay, but we'll be dealing with that part kind of separately. So the observations we need to make for this lab are as follows. We need to measure the height of our ramp, all right, because that'll help us to calculate our potential energy initial. We will need to measure the speed of the cart at the bottom of the ramp. To do that, we'll be using the SparkView motion sensors again. So the good news is you don't have to build a graph with this. You're just going to have to look at each trial and find the fastest speed. Okay, that's all you have to do, is just find the fastest speed and use that to calculate the kinetic energy of the cart at the bottom of the ramp. Okay. The other things you'll need to measure, and you won't be measuring them with the electronic equipment, you'll have to have somebody else doing this, is you're going to need to time the cart after it leaves the ramp until it stops. Okay, so someone's going to have to be watching. Okay, so a separate person from the person who's running the SparkView stuff. As soon as that cart leaves the ramp, they start the timer. They stop it when the cart actually stops. Okay, you'll need that time. And you'll need to mark where that cart stops on the floor and then measure it after. All right, so we'll need that distance and that time because that'll help us with our friction calculation. Okay. Nope, it's just going to go right off the end. There's a bit of a lip, but I mean, it's still energy, right? Energy works whether I'm off the ramp or if I'm falling straight down, so it'll all still work. Okay, everybody with me there? That's a good question. Okay, manipulated, responding, controlled variables. Remember, guys, that we are comparing here. Most of this lab just has to do with the conversion of the potential energy at the top into the kinetic energy at the bottom, right? This thing doesn't happen unless we do what? Lift it, right? I'm trying to sort of give you some help with the variables without outright giving them to you, okay? We are comparing the energy at the top of the ramp with the energy at the bottom of the ramp, okay? We have to give it one in order to have the other. For your controlled variables, again, you need to just be looking at what goes on the ramp, okay? Controlled variables that affect how the cart moves down the ramp. Okay, for our hypothesis, okay, we want to have something that's a tentative answer to the problem and explain why this is so. So I would say the way to go about this is something like this, okay? In the if part of your hypothesis, I would talk about the law of conservation of energy and what it says about this conversion. Okay, and I would say do that from a perspective of you live in the perfect physical world. Okay, what does the law of conservation of energy say about this conversion if you live in the perfect physical world? Okay, the and part, as always, describes the experiment. Cart's going down a ramp, converting one form of energy to another, something like that. Okay, the then part needs to tell me how they'll be, or what you're going to see at the bottom. Okay, am I going to have all, is it going to be moving at a high rate of speed? Is all the energy still going to be there? Okay, that kind of thing. So then predict your results at the bottom. All right, if we are looking at this experiment and this hypothesis from the point of view of being in the perfect physical world, are we going to be able to accept it at the end? No, because we're not running this in the perfect physical world. Okay, we have to keep that in mind, right? We're probably going to have to refute our hypothesis, and a big part of your conclusion in this lab is going to be explaining why. Okay, you're going to have a lot of real world explanation as to why did it not, Why was not all of the energy there at the bottom? Where did it go? Okay, what happened to it? Okay, so we know the observations, like we said, that you're going to have to make here are going to be that you're going to have the height of the ramp, speed of the cart at the bottom of the ramp, time for the cart to coast to a stop. That means after it leaves the ramp. Don't start it when it's on the ramp. Start it after it leaves the ramp. Okay, and the distance it travels from the bottom of the ramp, where only the force of friction is then working on it. Okay, those are the observations you need to make. Distance traveled after the ramp, time after the ramp, okay, height of the ramp, speed at the bottom of the ramp. 4 things, okay, got to have those. You need the mass of the cart, and I believe I put it here. The mass of the cart is 475 grams, or 0.475 kilograms would probably be the more useful number for you, since all of your calculations need it to be in kilograms. All right. So the setup's going to be pretty easy. Don't make the ramp very steep. If you make the ramp really steep, the cart will go too far and it'll hit stuff. Okay, we want to have this so that it's just high enough that we can still get good data. Okay, everybody with me on that? Okay. So I would say the height of these 3 textbooks, maybe the height of this first step. Okay, on this little stool here, okay, something like that. Don't make it too high. 1, maybe 2 binders will be lots. All right, now we should have room to do 1 or 2 of them in here. We might have to send a few people over to the lab in order to have room for their carts to run and all that kind of stuff. Okay, but really all you're doing is a few trials of the same thing just to get consistent data. All right, so we can kind of average them. Okay, so for the procedure here, we'll set up that ramp, place the dynamics card on there, okay, measure and record how far it travels from the bottom of the ramp, as well as, like we said, the height of the ramp and the maximum speed, okay, and do 4 trials in total. All right, so it says do 3 more. That's after the first one, so you're going to do a total of 4 trials on here. Okay, Calvin, question? Oh, do I only have 3 on there? Oh, then just do 3. Sorry, I couldn't remember how many I had on there. Okay, just do 3, and then we're going to average. Okay, the distance, the time. Oh, I forgot to. Okay, so what you will have to do is add in here, though, one more column for the speed. Right, for the speed at the bottom of the ramp. I forgot to add that in here. I modified this lab on Friday, and I forgot to add the speed of the cart. No, we just want to get consistent data. So we're doing 3 exact trials, 3 trials that are exactly the same, just for consistency. We're not changing the height of the ramp. Okay, we're going to make the height of the ramp the same for all 3 trials. We just want to get consistency in the data, in case we have one that's a little wonky or something like that. Yes, and they will be. I mean, I've done this lab a bunch of times, and like when that cart rolls to a stop, it's usually all the stopping points are within 30 centimeters of each other. Yeah. Well, it says velocity on the thing, but it's scalar. We're not taking the direction, right? All right, so yeah, just make sure you add in there another column here. I'll show you quickly how to do that. Okay, just move this over, and the table tools here. Okay, so just take this thing here. Oh no, that's not it. All right, where do I get that from? Okay, so this will be our column for speed. Not speedy, speed. Okay, and that'll be in meters per second as well. Okay. All right, so 3 trials, okay, record those things. Obviously, you only need to record the height once because you're not moving the ramp. Okay, the ramp's going to be the same. All those 3 trials should have numbers that are similar, which is why we're averaging them at the bottom. Okay, that'll help us to limit our calculations because we're just going to do one calculation with the averages when we're doing these calculations that are in the analysis here. Okay, so in the analysis, right, the questions are calculate the potential energy at the top of the ramp, show me your work. That's an easy calculation. Okay, calculate the acceleration of the cart after leaving the ramp. Okay, the formula for that is right here. So we're going to use, what we're actually using is this formula. Is like D equals VFT minus 1/2 AT squared. We're kind of using that. Okay, we're just going to manipulate it for A. Okay, so the formula we're using is just going to be this, just to simplify. Okay, so take 2 times your distance and divide it by T squared, and that'll give us the acceleration of the cart. Okay. Number 3, calculate the kinetic energy of the cart at the bottom of the ramp using the largest speed value that you get in the SparkView data. Okay, obviously you're using actually the average of the largest speed value from your chart. Number 4, you got to write a bit there. Okay, I want some explanation. Did the potential energy equal the kinetic? Why or why not? Suggest reasons for your results. I'm looking for several sentences there. All right, I want to see how in-depth your understanding is of what's going on here. All right, for number 5, this is now talking about after it leaves the ramp. So friction does all the work in stopping the cart, and the cart's mass is 475 grams. What is the coefficient of friction between the cart's wheels and bearings? Show your work. Okay, so you know what the friction formula is. You should be able to calculate that fairly easily. Okay, what can this lab tell us about the efficiency of mechanical energy conversions? Probably looking for a couple of sentences there as well. Okay, and number 7, what are some ways to increase the efficiency of this conversion? Just some ideas and how they would do that. So this is what I would do. This is why it would work. Okay, everybody follow me on that? Okay, and then you have your conclusion and evaluation, same as always. Okay, so restate your hypothesis. As we said, we're probably rejecting that unless something really outlandish happens. Okay, we should be rejecting that. And then obviously your sources of error, 2 of them, and ways to fix them. Yes, the initiating and planning is telling you how to do the calculations for here. Yeah, okay. All right, questions on that? All right, so we got 6 ramps. I think there's 6 of the proper carts here. So that's the black ones. Okay, use the black ones for the wooden. Hopefully there's 6 black ones that work in here. If not, we'll be down to 5. Okay, so just, yeah, grab them, grab a ramp, and like I say, not too tall, okay, about 3 books tall or so, and you're off to the races, okay?